Everything around us began with a single chemical bond. The story of the universe's first molecules is the ultimate origin story, and we are about to explore 30 of the most compelling theories that explain it. By the end, you will understand how the empty cosmos transformed into a chemical nursery capable of brewing life itself. We will investigate which molecule truly came first, and how something as fragile as a water molecule could form in the violent chaos of early space. What do you believe was the most important ingredient for our cosmic beginnings? Our cosmic story begins not with complex chains of atoms, but with a single, solitary bond. Picture the universe in its infancy, a searing hot soup of particles so energetic that atoms could not even hold together. For hundreds of thousands of years, it was just a plasma of protons, electrons, and the light nuclei of hydrogen and helium, all buzzing in a chaotic fog. Then a pivotal shift occurred as the cosmos expanded and cooled. Around 380,000 years after the Big Bang, electrons were finally captured by those lonely protons, forming the very first atoms. This was the moment neutral hydrogen and helium were born, but they were not yet molecules. The stage was now set for the next great act. In this new, cooler universe, the simplest chemical bond became possible. Two hydrogen atoms drawn together could share their electrons. This created molecular hydrogen, or H2. This simple pairing of two of the most abundant atoms was a monumental leap. It was the universe's first stable molecule, a quiet but profound beginning to all the chemistry that would follow. Yet there is a strong contender for an even earlier title. Many scientists theorize that the very first molecule of all was not hydrogen, but something more exotic, helium hydride. Imagine a universe still cooling from its fiery birth. A lone helium ion, a nucleus stripped of its electrons, drifts through the thinning plasma. It encounters a proton, the nucleus of a hydrogen atom. In that instant, they form a fragile bond, creating helium hydride, or HEH+. This ion is thought to have been the cornerstone, the very first molecular structure to ever exist. Its formation was a crucial first step, beginning the process of cooling the early universe and paving the way for the more complex molecules that would one day build stars, planets, and us. How did these delicate first bonds survive the violent aftermath of creation to seed the cosmos with chemistry? But that first fragile bond did not form in a perfectly smooth cosmos. The very structure of our universe, the vast cosmic web of galaxies and the emptiness between them, was essential for chemistry to take root. This structure owes its existence to a theory known as cosmic inflation. In the tiniest fraction of a second after the Big Bang, the universe underwent an unimaginably rapid growth spurt, expanding faster than the speed of light. This inflation did not just make the cosmos enormous, it also made it incredibly smooth and uniform. Yet it was not perfectly smooth. On the smallest possible scales at the quantum level, tiny fluctuations were inevitable. As the universe inflated, these microscopic ripples were stretched to astronomical sizes. They became the subtle variations in density, the slightly denser patches in the primordial soup of matter and energy. These minute differences in density were the seeds of everything. Without them, the universe would have remained a featureless, thin haze, with matter spread so evenly that molecules might never have found each other. These tiny overdense regions acted as gravitational anchors. They began to gently pull matter inward, creating the first potential wells where hydrogen and helium could gather. It was within these gathering clouds that the first molecules found their home. The slight increase in density meant atoms were closer together, making those first tentative chemical bonds far more likely to occur. This cosmic preparation, set in motion by inflation, was the essential prelude. It created the nurseries where molecular hydrogen could form in abundance, cool the gas, and eventually collapse under gravity to ignite the very first stars, lighting up the dark cosmos for the first time. This era of profound darkness was far from empty. For millions of years, the universe entered a cosmic quiet period, a time after the first atoms formed and before the first stars sparked to life. Scientists call this the cosmic dark ages. The brilliant fireball of the Big Bang had faded to a uniform, dim glow, a remnant microwave background that permeated all of space. In this vast, silent expanse, the real work of molecule building began in earnest. With stable neutral atoms now populating the cosmos, the stage was perfectly set for them to find each other. The dominant process was a slow, quiet accumulation. Vast clouds of primordial gas, composed almost entirely of hydrogen and helium, drifted through the expanding darkness. Within these clouds, pairs of hydrogen atoms began to link up. The formation of molecular hydrogen, or H2, was a delicate dance. It could not happen through a simple collision, as two atoms would just bounce apart. Instead, the bond required a third partner, another atom or particle, to carry away the excess energy from the collision, allowing the two hydrogens to stick together. This three-body process was rare and slow, but over millions of years, it gradually converted a small but crucial fraction of the universe's atomic hydrogen into its molecular form. This was a silent, invisible transformation, the universe's first chemical industry operating in the dark. Why was this slow accumulation so vital? Because molecular hydrogen is a remarkably efficient coolant. As these early gas clouds slowly collapsed under their own weak gravity, the H2 molecules inside them were able to radiate away heat. This cooling allowed the clouds to condense further, growing denser and denser until they reached a tipping point. The Dark Ages were not a stagnant pause, but a period of patient gravitational preparation, all made possible by the quiet, persistent formation of the universe's first abundant molecule. What cataclysm would finally shatter this cosmic silence and change everything? That triumphant discovery, however, was the end of a very long hunt for a molecule that started it all. While molecular hydrogen was the first abundant molecule, many scientists point to an even more primordial candidate, the helium hydride ion. Its chemical formula is HEH+. To form this pioneer, you need the raw ingredients of the early universe in their most basic forms. A bare helium nucleus, which is an alpha particle, and a lone proton, which is a hydrogen ion, must find each other in the cooling plasma. When they collide, the helium nucleus can share its space with the proton, creating the first true chemical bond in existence. This was not just a simple pairing, it was the spark that ignited all of cosmic chemistry. HEH+ is what chemists call a proton donor, an acid in the most fundamental sense. This property made it a cosmic catalyst. It could go on to react with the neutral hydrogen atoms that were beginning to fill the universe, transferring its proton, and in the process creating the first molecular hydrogen ions. Those ions could then react further, building the foundation for all subsequent chemistry. This single molecule set in motion the entire molecular evolution of the cosmos. For decades, this was purely theoretical. The challenge was that helium hydride is incredibly fragile and reactive. It cannot survive for long in most modern environments. Astronomers searched for its telltale signature in distant space, a specific frequency of light it emits, but found nothing. The molecule that started everything seemed lost to time. The breakthrough came in 2019. Scientists using a high-altitude observatory called SOFIA, a telescope mounted inside a jumbo jet, finally detected the faint signal of HEH+. They found it not in the ancient universe, but in the wreckage of a dying star, a planetary nebula. The conditions there, harsh and hydrogen-rich, perfectly mimicked the chemistry of the early cosmos. This observation was a monumental confirmation. It proved that the theory was correct, that this simple ion was not only possible, but was indeed a fundamental player in the chemical dawn. If helium hydride was the initial spark, what came next in the chain reaction that built a chemical universe? That detection of helium hydride was the final piece of a puzzle that confirmed the starting gun for cosmic chemistry. But the real workhorse, the molecule that truly built the cosmos, was molecular hydrogen. While HEH+ provided the initial spark, H2 became the engine. Its formation, however, required more than just chance encounters in the dark. In the vast, sparse clouds of the early universe, two hydrogen atoms could not simply stick together. They needed help. One of the most important theories suggests this help came from the first solid surfaces in the cosmos, microscopic dust grains. Picture a tiny, floating speck of carbon or silicate, a cosmic mote. When a hydrogen atom bumps into this grain, it can stick, bouncing around on the surface like a pinball. If a second hydrogen atom lands nearby, the two can find each other, link up, and then drift away as a single, stable H2 molecule. This process on the surfaces of dust was a molecular assembly line, far more efficient than the rare three-body collisions in pure gas. It was a quiet, continuous production, turning the raw atomic fuel of the universe into its molecular form. This transformation was not just about quantity, it was about capability. Molecular hydrogen possesses a special talent that atomic hydrogen lacks. It can cool a gas cloud. Think of H2 as the universe's first and most vital air conditioning system. As a cloud of gas begins to collapse under its own gravity, it heats up. This heat creates an outward pressure that fights against further collapse. Atomic hydrogen is very poor at radiating this heat away, but an H2 molecule, with its two atoms vibrating and rotating, can release energy in the form of infrared light. It effectively radiates the heat away into the cold of space. This cooling allows the cloud to continue condensing, growing denser and hotter at its core. Without this crucial cooling effect, the first gas clouds would have simply heated up and stabilized, never reaching the incredible densities and temperatures needed to ignite nuclear fusion. The relentless work of H2 molecules, formed on cosmic dust or in gas phase reactions, was the essential step that allowed gravity to win. It enabled the great collapse that lit the first stars, ending the cosmic dark ages and flooding the universe with light for the very first time. What did these first stellar furnaces create from the simple ingredients of hydrogen and helium? While molecular hydrogen was the undisputed workhorse, another simple molecule may have played a crucial, if more subtle, supporting role. This brings us to the lithium hydride hypothesis. In the primordial soup forged by the Big Bang, alongside the vast oceans of hydrogen and helium, there existed only trace amounts of a few other elements. One of these was lithium. The theory suggests that some of this lithium, the third lightest element, could have combined with the abundant hydrogen to form lithium hydride, or LiH. While it would have been vastly outnumbered by molecular hydrogen, LiH possesses a unique and powerful property. It is an extremely efficient radiator of energy, particularly effective at cooling the universe at very specific low temperatures. Think of it as a specialized cooling unit operating in a different range than the more general H2. In the cold, collapsing gas clouds of the late Dark Ages, even a tiny fraction of LiH molecules could have significantly enhanced the cooling process. They would have acted like microscopic radiators, helping certain regions of gas shed heat more effectively and collapse faster into the seeds of the first stars. This makes lithium hydride a theoretically important player, a catalyst that might have accelerated cosmic evolution in key areas. Despite its significance in theory, finding direct evidence has been a monumental challenge. Because it was so rare and its formation depended on specific conditions, its fingerprint in the early universe is incredibly faint. Astronomers continue to search for the telltale signature of LiH in the light from the most distant quasars, using high redshift observations to peer back in time. The ongoing hunt for this elusive molecule is a testament to its potential importance, a quest to confirm whether this minor ingredient had a major impact on shaping the cosmos. Yet, even as these first molecules began their quiet work, a heavier version of hydrogen was waiting in the wings. This is deuterium, a fascinating isotope that carries an extra neutron in its nucleus. While most of the universe's hydrogen was the common, lightweight variety, the Big Bang left behind a small but significant supply of this heavier cousin. It was only one deuterium atom for every few tens of thousands of regular hydrogen atoms, but that was enough to change the chemical landscape. Theorists propose that deuterium could have formed its own unique set of pioneer molecules, and these deuterated species might have been even more efficient at getting started. Consider the simple swap of one hydrogen atom for a deuterium one. This creates hydrogen deuteride, or HD. The bond in HD is slightly stronger than the one in regular molecular hydrogen. This small difference in binding energy was a huge advantage in the sparse early universe. A stronger bond means that when two atoms collide, they are more likely to stick together rather than bounce apart. This made the formation of HD and its fully deuterated cousin, D2, potentially more efficient than the formation of H2 in certain cold, low-density environments. They were the robust, hardy pioneers, forming more readily where their common relatives struggled. This robustness made them far more than just chemical curiosities. For modern astronomers, these deuterium-based molecules are priceless cosmic fossils. Because they form so efficiently under specific conditions, their abundance acts as a perfect tracer. By measuring the amount of hydrogen deuteride in a distant gas cloud, scientists can effectively take the temperature and measure the density of that primordial gas. It is like finding a preserved thermometer from the dawn of time, giving us direct insight into the physical conditions that existed long before the first stars were born. The subtle signature of deuterium, imprinted on the first molecules, provides a unique window into the cold, dark nursery where everything began. The strength of a deuterium bond, however, was not the only path to stability. In the absolute void before dust grains existed, another, more fundamental process was at work. This is the three-body association problem, a cornerstone theory for how the first bonds were forged in pure, empty space. The challenge was simple yet profound. When two hydrogen atoms collide, they do not simply stick. Their mutual attraction brings them together, but the energy of their collision makes them bounce right back apart, like two perfect magnets that repel on contact. To form a stable bond, that extra energy must be carried away. The solution required a third actor. In a three-body association, two hydrogen atoms approach each other, and at the precise moment of their closest encounter, a third particle, often another hydrogen atom or a free electron, collides with them. This third body acts like a sponge, absorbing the excess energy from the collision and flying away. With that energy gone, the two original atoms no longer have the force to push apart. They are left linked, a stable molecule of H2. Think of it as a three-person handshake where the third person's role is not to join the bond, but to stabilize it by taking the energetic jolt away. This process was incredibly inefficient and slow, a rare cosmic coincidence that had to happen countless times to build up any significant amount of molecular hydrogen. Yet in the vast, patient expanse of the Dark Ages, this inefficient mechanism was utterly essential. It was the primary way the very first molecular hydrogen formed before there were any solid surfaces in the universe to aid the process. This counterintuitive dance of three particles to make one bond set the entire chemical future in motion. How could such a slow and fragile process possibly build a universe? This slow, patient accumulation faced a constant, invisible threat. The young universe was still bathed in the fading afterglow of the Big Bang, a pervasive sea of high-energy photons. While this light was no longer the searing fireball of creation, it remained intense enough to act as a universal shredder for delicate molecular bonds. This was the photodissociation barrier, a relentless force that could tear molecules apart as quickly as they formed. Imagine trying to build a delicate house of cards in a room filled with constant, gentle breezes. Each time two atoms managed to link up, a stray photon, a particle of light, could slam into them. This impact would inject energy back into the bond, violently shaking the two atoms apart. For millions of years, this created a frustrating cosmic stalemate, with formation and destruction locked in a fragile balance. So how did any molecule ever gain a permanent foothold? The answer lies in the search for cosmic shadows. The early universe, while broadly uniform, was not a perfectly smooth void. Those tiny density fluctuations from inflation had grown into the first faint structures. As hydrogen and helium gathered into vast, diffuse clouds, these clouds themselves began to act as shields. The outer layers of a cloud would absorb the destructive high-energy photons, sacrificing their own molecules to protect the interior. Deep within these cosmic nurseries, pockets of gas existed in relative darkness, shielded from the relentless background radiation. It was in these sheltered cores that molecular hydrogen could form and, crucially, persist. This was not a single event but a gradual process. As the universe expanded and cooled further, the background radiation itself lost energy, becoming less and less effective at breaking bonds. The balance slowly tipped in favor of creation. The first molecules did not form everywhere at once. They survived in the safe havens, the protected niches where darkness first fell. This delicate dance between light and shadow was essential, ensuring that the seeds of chemistry were not erased before they could ever sprout. What other cosmic phenomena provided the shelter needed for these first molecular bonds to take root? These cosmic shadows found their ultimate ally in the first solid matter in the universe. The theory of dust grains as molecular factories proposes that the most efficient chemical workshops were not in the empty void, but on the surfaces of microscopic particles. Before the first stars died, where did this dust even come from? The very first grains were likely forged in the violent, energetic outflows of the first giant stars, or perhaps even in the frigid atmospheres of aging, carbon-rich stars that formed later. These specks, smaller than a wavelength of light, were composed of simple materials like amorphous carbon or silicates, the same stuff that makes up soot and sand. They were the first solid ground in a cosmos of gas. An atom drifting through space would eventually collide with one of these grains and simply stick, held by weak chemical forces. It would wander across the surface until it met another atom. On this solid stage, the delicate dance of bond formation became profoundly easier. Instead of requiring a rare three-body collision in open space, two atoms could meet and link up on the grain, with the solid surface itself acting as the third body that absorbed the excess energy. The newly formed molecule, now with enough energy to escape the grain's weak grip, would be released back into the gas. This process turned each microscopic dust particle into a relentless, automated assembly line, churning out molecular hydrogen with an efficiency the pure gas phase could never match. This was the universe's first industrial revolution, hidden inside dark clouds. By providing a solid anchor, cosmic dust did not just make molecules faster, it made entirely new kinds of chemistry possible. It allowed for the formation of the most fragile molecular bonds, the kinds that could never survive a violent collision in open space. These tiny grains, nearly invisible to our telescopes, were the unsung heroes of chemical complexity, silently building the foundations for everything that was to come. Deep within these dark, dusty nurseries, gravity began to weave its magic. As a protostellar cloud collapsed, its core underwent a dramatic transformation. The simple, sparse gas of the intergalactic medium was now a churning, dense maelstrom. This was no longer a passive environment. It was a cosmic pressure cooker where chemistry was supercharged. The immense gravitational energy of the collapse did not just pull matter inward. It converted into intense heat, raising the temperature of the gas from just a few tens of degrees to hundreds, and then thousands of degrees. In the cold, diffuse void, only the simplest reactions could occur. But here, in the heart of the cloud, the heat provided the activation energy for entirely new classes of chemical reactions. Atoms and molecules, now packed incredibly close together and buzzing with thermal energy, collided with far greater force and frequency. This turbulent heat unlocked chemical pathways that were previously sealed shut. Where two hydrogen atoms might have gently bounced apart in deep space, they now slammed together with enough vigor to form robust H2 molecules at a staggering rate. But the story did not end with hydrogen. For the first time, the inert noble gas helium, a chemical recluse that refused to bond under normal conditions, found itself forced into partnerships. The intense heat and density created just enough energy to allow helium to interact with other ions, hinting at the reformation of those primordial helium hydride ions right there in the stellar womb. This was the universe's first true chemistry set, moving beyond simple pairings and into the realm of ion chemistry and endothermic reactions, all fueled by the raw power of gravitational collapse. How far could this molecular complexity go before the first star ignited and wiped the slate clean? The intense chemistry within those collapsing clouds was merely a prelude to a far greater explosion. The first stars did not just live, they died in spectacular fashion, and their deaths were the true catalysts for a chemical revolution. When a massive star exhausted its nuclear fuel, its core collapsed in a cataclysm known as a supernova. This was not merely an end, it was the most important distribution event in cosmic history. The blast-forged elements that the Big Bang alone could never have created. In the heart of that unimaginable inferno, atomic nuclei smashed together with such force that they fused into entirely new elements. Carbon, the backbone of life, was born here. Oxygen, the breath of complex organisms, was forged in this fire. Nitrogen, silicon, and even iron were blasted out into the void. This process, called metals enrichment by astronomers, fundamentally changed the composition of the universe. For the first time, the periodic table expanded far beyond its primordial simplicity. The cosmos was no longer a domain of just hydrogen and helium. It was now seeded with the raw ingredients for true complexity. These new elements did not just float alone. As the supernova remnant expanded and cooled, these atoms began to find each other. Carbon could now bond with hydrogen, forming stable molecules like methane. Oxygen could link with hydrogen, creating the first true water molecules in deep space. Silicon and oxygen could join to form the seeds of future dust grains, the very silicates that would become the bedrock of planets. This was a quantum leap in chemical potential. The simple two-atom molecules of the Dark Ages were now joined by a menagerie of new compounds. Carbon monoxide, water, ammonia, and formaldehyde began to appear in the cooling stellar ashes. These molecules were the new toolkit for the universe, possessing a wider range of properties than hydrogen or helium hydride ever could. They were better at cooling gas, they could form more complex structures, and they carried the potential for the chemistry of life itself. This enrichment was not a one-time event. Each generation of stars lived, died, and polluted the interstellar medium with these heavier elements, ensuring that the next generation of stars and planets would be born from a richer, more chemically diverse stock. The violent death of the first stars was, paradoxically, the creative act that filled the cosmos with the building blocks for everything we know. That chemical enrichment from the first supernova set the stage for a molecule we often take for granted. Among the new elements forged in stellar furnaces, oxygen was a key player, and its journey to bond with hydrogen created the most famous molecule in the cosmos, water. The formation of H2O in space is a story of patience and perfect conditions. One primary pathway is a direct gas phase reaction. In the wake of a supernova, free oxygen atoms mingle with the abundant molecular hydrogen. A collision can break the H2 bond, allowing one oxygen atom to grab two hydrogen atoms, forming a single water molecule. This process is efficient in warm, dense regions where particles collide with enough energy to initiate the reaction. Yet another, perhaps more prolific, pathway occurs on the surfaces of interstellar dust grains. Picture a tiny silicate grain, a speck of stardust drifting through a cold cloud. An oxygen atom lands and sticks to its surface. Soon after, a hydrogen atom arrives, wandering across the grain until it finds the oxygen. They link up, creating a hydroxyl radical, OH. Then, a second hydrogen atom arrives, completing the transformation into a full water molecule. The grain's surface provides the stable platform this delicate assembly requires. Once formed, the water can be released by a slight warming or a photon's nudge, launching it into the gas. This makes dust grains incredible molecular factories, potentially responsible for creating vast reservoirs of water ice that coat grains in dense molecular clouds. Why is the hunt for this ancient water so critical? Because water is far more than a simple solvent. It is a fundamental actor in prebiotic chemistry. Its unique polarity allows it to dissolve other molecules and facilitate complex reactions, the very kind that could lead to amino acids and sugars. Discovering water in the most ancient, primordial clouds would tell us that the essential ingredient for life was present almost from the beginning, woven into the fabric of the universe long before planets ever formed. But even within the protective shadows of those dark clouds, another source of energy was at work. Cosmic rays, high-energy particles racing across the galaxy at nearly the speed of light, provided a constant, penetrating spark. These are not rays of light, but atomic nuclei, mostly protons, ejected by supernovae and other violent cosmic events. When one of these bullets slams into a cold, dark molecular cloud, it does not just bounce off. It plows right through, tearing electrons from the atoms and molecules in its path. This ionization process is like throwing a lit match into a room full of flammable gas. A molecule of molecular hydrogen sitting quietly is suddenly blasted apart. It loses an electron, becoming a positively charged ion, H2+. This ion is no longer stable or passive. It is wildly reactive, desperate to regain its balance. It will aggressively seek out another molecule, perhaps a neutral H2, and in an instant it can trigger a chain reaction. The collision creates an H3+ ion, a simple yet profoundly important molecule made of 3 hydrogen atoms. H3+ is a cornerstone of interstellar chemistry, a potent proton donor that can go on to transfer its extra proton to almost any other atom it meets, be it oxygen, carbon, or nitrogen. This single reaction, initiated by a cosmic ray, can set off a cascade, building molecules like water, methanol, and formaldehyde in the deep cold of space where there is no starlight to provide energy. Cosmic rays turn the entire interstellar medium into a vast, low-temperature chemical reactor, proving that the seeds of complexity could grow even in the deepest cold and darkest voids. Carbon offered a path to complexity far beyond simple chains of water and ammonia. Among the most fascinating and controversial theories is the idea that large, stable carbon structures existed almost from the beginning, a concept known as the PAH world hypothesis. PAH stands for polycyclic aromatic hydrocarbon. While the name sounds complex, the structure is something you encounter every day. Picture the soot from a candle flame, the black char on a piece of burnt toast. At the molecular level, that soot is made of PAHs. They are flat, stable molecules like tiny chicken wire mats made of interlocking rings of carbon and hydrogen atoms. The theory proposes that these were not latecomers, but some of the first large organic molecules to form in the universe. They are thought to have been forged in the fiery, carbon-rich atmospheres of aging red giant stars. As these stars near the end of their lives, they puff off their outer layers in vast cosmic winds. In these expanding shells of gas, conditions are perfect for carbon atoms to link up into the robust, ringed structures of PAHs. These molecules would then be blown out into the interstellar medium, becoming a fundamental component of the earliest cosmic dust. Their flat, sturdy shape made them incredibly resilient, allowing them to survive the harsh radiation of space far better than more fragile molecules. But why would these soot-like specks be so important? Because a PAH molecule is not an endpoint, it is a platform. Its sprawling surface of carbon rings is a perfect landing pad for other atoms and small molecules drifting through space. On this stable stage, new chemical bonds could form, building outward from the PAH core. A simple PAH could, over time, be decorated with side chains of other atoms, potentially evolving into the precursors of life's essential building blocks, like the nucleobases found in DNA. In this view, PAHs were not just dust, they were the universe's first probiotic construction sites, offering a stable foundation upon which the chemistry of life could begin to experiment. These carbon scaffolds set the stage for the most profound leap of all, the moment when cosmic chemistry crossed the threshold into biology. The journey from soot to life is theorized to have passed through a crucial intermediate stage known as the RNA world. This hypothesis suggests that before DNA and proteins, life was based on a simpler, more versatile molecule, RNA. RNA can both store genetic information, like DNA, and catalyze chemical reactions, like a protein. It was the universe's first all-in-one tool kit. But where did the building blocks for this miraculous molecule come from? The answer may lie in the chemistry of interstellar space itself. Within the frigid, dark molecular clouds on the surfaces of dust grains and PAHs, the basic ingredients for RNA were likely being assembled. Simple sugar molecules like glycolaldehyde have been detected in star-forming regions. These sugars are the ribose backbone of RNA. Even more remarkably, astronomers have found hints of nucleobases, the information-carrying letters of RNA, in meteorites that have fallen to Earth. The raw materials for a genetic system were being cooked in the cold void of space, long before the Earth even formed. How did these delicate organic molecules survive a journey across the solar system to reach our young planet? They hitched a ride on cosmic delivery vehicles. Comets, asteroids, and meteorites became the freight trains of probiotic chemistry. A comet is essentially a dirty snowball, a frozen repository of water ice, dust, and complex organic molecules that has remained largely unchanged since the solar system's birth. When such a body impacted the early Earth, it did not just bring water. It delivered a rich inventory of pre-formed organic compounds, including the very sugars and nucleobases needed to build RNA. This theory of panspermia, not of life itself but of life's ingredients, suggests our planet was seeded from the stars. The violent impact of a comet would have created a warm, watery pond, a perfect nursery where these delivered molecules could mix and concentrate. Under the right conditions, they could have linked together to form the first self-replicating strands of RNA, launching the great experiment of life on Earth. The first molecules of the cosmos, born in the ashes of stars and assembled on interstellar dust, may have ultimately written the first genetic code. Beyond the chaos of cosmic rays and the shelter of dust, a more subtle force was weaving order into the chaos. Weak magnetic fields, relics from the universe's earliest moments, threaded their way through the primordial gas. As the first molecules began to form, these fields exerted a gentle but persistent influence. A drifting hydrogen molecule, tumbling randomly through space, would feel this invisible hand. The magnetic field could nudge the molecule, causing it to spin along a preferred axis, aligning it with the field lines like a compass needle pointing north. This was not a violent process, but a quiet ordering of the molecular chaos. In the vast, dark clouds where stars are born, this alignment became a universal phenomenon. Countless molecules, all spinning in concert, created a unique signature. When light from a distant star or the cosmic microwave background passed through such a cloud, these spinning molecules interacted with it in a special way. They would scatter the light, imprinting it with a specific direction, a property known as polarization. This polarized light is the key for astronomers. It acts as a cosmic messenger, carrying information about the magnetic field that aligned the molecules. By meticulously measuring the polarization of starlight, scientists can trace the shape and strength of these invisible magnetic skeletons within interstellar clouds. This reveals how magnetic fields guide the collapse of gas, channeling flows and influencing the very birth of stars. The humble alignment of the first molecules provides a window into the hidden architecture of the cosmos, a framework that shaped everything that followed. This invisible magnetic architecture hints at a far deeper cosmic secret. Most of the matter in the universe does not glow, spin, or interact with light at all. It is the mysterious substance we call dark matter, and its true nature remains one of the greatest puzzles in science. A bold and highly speculative theory proposes that dark matter could have its own hidden chemistry. We know it must possess mass and respond to gravity, but what if certain types of dark matter particles could also interact with each other through some unknown, feeble force? This would open the door to the existence of dark molecules. Picture hypothetical particles like actions or WIMP, weakly interacting massive particles. While they pass right through ordinary matter as if it were not even there, they might feel a subtle pull from their own kind. If this force were just strong enough, two actions could theoretically bind together, forming the dark matter equivalent of a hydrogen molecule. These would not be molecules made of atoms, but of something far more exotic, held together by a force we have yet to discover. The implications of such a discovery would be staggering. It could explain why dark matter clumps in the specific ways we observe, forming the vast, invisible halos that cradle galaxies. The presence of dark molecules could change how this mysterious substance cools and collapses under gravity, potentially solving long-standing discrepancies between our computer simulations and the real universe we see. Of course, this idea remains on the farthest frontier of theoretical physics, a ghost of a possibility. We have no direct evidence that dark matter is anything other than a sea of solitary particles. Yet the mere possibility ignites a profound question. Could there be an entire, invisible chemical universe existing in parallel to our own, a shadow realm of molecular structures built from the stuff that binds the cosmos together? The brilliant light of the first stars did not just build the cosmos, it also tore it down. These stellar giants flooded space with a specific, potent form of ultraviolet radiation known as Lyman-Werner photons. This light carried just the right amount of energy to perform a delicate and destructive surgery on the molecular hydrogen clouds that gave these stars life. When a Lyman-Werner photon struck an H2 molecule, it did not simply break the bond. Instead, it pumped energy into the molecule, exciting it to a higher state, only for it to decay and shatter into two separate hydrogen atoms. This process, called photodissociation, acted like a universal off switch for star formation. In regions bathed in this harsh stellar glare, the molecular hydrogen that was so crucial for cooling and collapse was systematically dismantled. The very engine of creation was being dismantled by its own children. This created a complex feedback loop, a self-regulating mechanism that governed the pace of cosmic evolution. Imagine vast bubbles of ionization expanding around clusters of massive stars. Inside these bubbles, the intense radiation field sterilizes the surrounding gas, breaking apart the H2 and halting the birth of new stars. It is a case of cosmic infanticide where the first generation of stars suppresses the next. Yet, this destructive force also contained a creative spark. At the edges of these expanding bubbles, something remarkable can occur. The blast of radiation and the shockwaves from stellar winds do not just destroy, they also compress. The immense pressure can slam into nearby, undisturbed clouds of atomic hydrogen, squeezing them violently. This compression can trigger a runaway collapse in the cloud's shielded interior, rapidly boosting the formation of new molecular hydrogen and igniting a new burst of star formation in the surrounding shell. So the same stellar radiation that quenches star birth in one place can simultaneously trigger it in another. This feedback loop, driven by the humble Lyman-Werner photon, became a fundamental governor, preventing the universe from burning through its fuel too quickly and instead orchestrating the structured, clustered growth of galaxies we see today. This bottom-up assembly of the cosmos was orchestrated by a powerful organizing principle known as hierarchical structure formation. The universe did not build galaxies in one grand, top-down sweep. Instead, it constructed its grand design from the smallest pieces upward. It all started with those first, faint ripples in the fabric of spacetime, the quantum seeds from the dawn of inflation. Gravity worked on these tiny overdensities, patiently pulling in the surrounding dark matter and primordial gas. The very first structures to condense out of the expanding cosmos were not mighty galaxies, but small, dark halos of matter, each containing a cloud of hydrogen and helium gas. It was within these modest, isolated nurseries that the first molecules truly found their footing. Shielded from the harsh background radiation, molecular hydrogen could form and begin its vital work of cooling the gas. This cooling allowed these small clouds to condense further and collapse, igniting the very first tiny population 3 stars. This was the foundational level of cosmic construction. But gravity is a relentless collector. These small halos, each perhaps hosting a single star or a small cluster, did not remain isolated for long. They were drawn together by their mutual gravitational attraction, spiraling toward one another in a slow cosmic dance. They would merge, their dark matter halos fusing into a larger structure and their gaseous contents colliding and mixing. This merger process was the engine of growth. A dozen small clouds could merge into a larger protogalaxy, and dozens of those could assemble into a small galaxy like the Magellanic Clouds orbiting our own Milky Way. With every merger, the chemical landscape was transformed. The molecular clouds from different halos would slam together, their gases colliding with tremendous force. These collisions did not just create chaos, they triggered intense waves of new star formation. Each merger shook up the settled gas, compressing it and igniting a new stellar baby boom. This repeated cycle of assembly and collision had a profound effect on cosmic chemistry. The first generation of stars born in small halos lived short, violent lives and exploded as supernovae, enriching their immediate surroundings with the first heavy elements. When that halo merged with its neighbors, it did not just contribute raw mass, it donated a payload of enriched material. Carbon, oxygen, and iron from one cloud would mix with the pristine hydrogen and helium of another. This created a rich chemical gradient across the growing galaxy. The center of a merging system where the gas was densest would become a hub of complex molecule formation, with water, carbon monoxide, and organic compounds appearing in abundance. Meanwhile, the outer regions might remain relatively pristine, still dominated by simple molecular hydrogen. This hierarchical process is why we see such a stunning diversity of cosmic environments today, from the metal-rich, molecule-packed cores of giant galaxies to the simple, ancient gas clouds lingering in the galactic outskirts. The entire cosmic web, with its vast filaments and dense clusters, was built through this patient, bottom-up assembly, with the humble first molecules acting as the essential catalyst at every single step. The hierarchical assembly of the cosmos was fueled by a hidden river system. While gravity pulled galaxies together, they needed a constant supply of fresh gas to sustain their growth, and the theory of cold accretion flows explains this cosmic delivery network. Picture vast, dark filaments of the cosmic web, not as empty voids, but as flowing rivers of cold, dense primordial gas. These streams, composed almost entirely of pristine hydrogen and helium, snaked through the expanding universe, channeling material directly into the hearts of the first growing galaxies. This was a vital shortcut, Earlier models suggested that gas falling into a galaxy would first shock heat to millions of degrees in a vast hot halo, requiring eons to cool back down before it could form stars. But cold flows changed the story entirely. These dense, narrow filaments were so efficient at radiating away their energy that they remained cold. They pierced straight through the hot halo like icy aqueducts, delivering their cool, raw fuel directly to the galactic core. This process created a perfect environment for molecule building on a massive scale. As these rivers of cold gas poured into the turbulent center of a young galaxy, they collided and mingled with gas that had already been enriched by earlier generations of stars. The resulting shock fronts and increased density created ideal nurseries for a new wave of molecular formation. Vast clouds of molecular hydrogen condensed from the flow, and within them, the enriched chemistry from previous stellar cycles could now work on a much larger canvas, forming complex molecules like carbon monoxide and water in unprecedented quantities. This continuous infusion of pristine gas was the lifeblood of the early universe. It did not just fuel star formation, it regulated it, ensuring that galaxies could grow steadily without burning through their fuel too quickly. The cold flows were the great sustainers, connecting the isolated molecular nurseries of the first small halos to the bustling chemical factories of the first true galaxies, weaving the universe together with threads of cold, primordial gas. These dark matter mini-halos were the universe's first true chemical laboratories. Long before the majestic spiral galaxies we know today took shape, gravity was working on a much smaller, more intimate scale. It pulled together the first clumps of dark matter, creating structures known as mini-halos. Though they were small by cosmic standards, these halos provided something the vast, empty void could not, a deep gravitational well. This well was the key that unlocked efficient chemistry. As the primordial gas of hydrogen and helium was drawn into these halos, it became denser and denser. This increased density was a game-changer for molecule formation. Atoms that would have drifted past each other in the intergalactic medium were now forced into close quarters, colliding far more frequently. Within the protective darkness of these mini-halos, the formation of molecular hydrogen shifted from a rare, chance event to a systematic, efficient process. The deep gravitational potential trapped the gas, allowing it to cool and condense for eons without being blown apart. This was the crucible where the first stars were forged. These are known as Population 3 stars, the true pioneers of stellar creation. They were not born in grand galaxies, but in these modest, isolated cradles. The mini-halos provided the stable, shielded environment where molecular hydrogen could cool the gas to the critical point of collapse. Without these first gravitational anchors, the gas might have remained too hot and diffuse, forever delaying the dawn of starlight. So the story of galactic chemistry does not begin with galaxies at all. It begins in these forgotten, dark matter cradles where the first molecules gathered in the shadows and lit the cosmic dark. The quiet assembly of those first molecules was governed by rules far stranger than those of any chemistry lab. In the deep cold of the early universe, atoms simply did not have the thermal energy to climb over the energy barriers required for a reaction. A classical collision would see them bounce apart every single time. Yet they still bonded, and one of the most fascinating theories explains this through a purely quantum effect known as tunneling. Think of the energy barrier not as a hill to be climbed, but as a solid wall. In our everyday world, if you throw a ball at a wall, it bounces back. You would never expect it to simply appear on the other side. But in the quantum realm, particles like protons and electrons behave as both particles and waves. A wave does not always reflect perfectly from a barrier. A tiny portion of it can seep through to the other side. This means there is a small but real probability that a particle can vanish from one side of an energy wall and instantly reappear on the other, as if it dug a tunnel straight through. It did not physically bore a hole, it exploited the fundamental fuzziness of reality at the smallest scales. This was not a rare event in the primordial cosmos, it was essential. At temperatures just a few degrees above absolute zero, tunneling was the only way for many crucial reactions to proceed. It allowed a proton to tunnel right into a helium ion to form that first helium hydride bond. It enabled two hydrogen atoms to ignore their mutual repulsion and fuse into molecular hydrogen. This quantum cheat code bypassed the classical rules that should have kept the universe a sterile soup of separate atoms. The entire chemical future of the cosmos depended on this subtle statistical magic, a silent permission slip from the quantum world that allowed bonds to form in the deepest cold. These quantum tunnels operated within a universe already etched with a vast, invisible pattern. The subtle ripples from inflation did more than just seed galaxies, they also set the cosmos ringing like a bell. This cosmic echo is known as the Baryon acoustic oscillation, a phenomenon that left a permanent fingerprint on the distribution of all matter, including the very first molecules. In the first few 100,000 years, the universe was a hot, dense plasma, a fluid of light and matter. In this searing soup, gravity tried to pull the atoms inward, but the intense radiation pressure from the photons of light pushed them outward. This created a tug of war, generating powerful sound waves that raced through the plasma at over half the speed of light. Then, the universe cooled past a critical point. Atoms formed and the photons, now freed, streamed away as the cosmic microwave background. The sound waves instantly froze in place, halting their expansion. This left a cosmic fossil, a preferred scale imprinted across the entire sky. Imagine dropping a pebble into a still pond. The ripples expand outward in a perfect circle until they freeze solid, preserved for all time. The Baryon acoustic oscillation is that frozen ripple on a cosmic scale. The size of this ring is staggering, nearly 500 million light-years across. This became a fundamental unit of cosmic construction. Where did this leave the first molecules? The frozen sound waves did not just affect dark matter, they organized the ordinary matter from which molecules are made. These oscillations created vast, spherical shells of slightly enhanced density, like the crest of a frozen wave. It was within these specific shells, these cosmic hotspots, that the conditions were perfect for molecule formation. The gas was just a little denser here than in the voids between the shells. This minute increase in density made all the difference. Atoms were closer together, making those initial chemical bonds far more likely to occur. So, the very first molecular hydrogen and helium hydride did not form in a random, uniform haze. Their distribution across the universe was subtly patterned, following the ghostly architecture of these ancient sound waves. They would have been more abundant within these immense spherical shells, creating rings of enhanced chemistry on a scale almost too large to comprehend. This means the blueprint for the cosmic web and the chemical richness within it was set in stone by the fading echo of the Big Bang itself. How could we ever hope to detect this faint primordial pattern in the modern universe? These ghostly rings of enhanced chemistry were not confined to galaxies alone. A radical idea suggests that molecules drifted freely in the cosmic voids, a diffuse population adrift in the immense intergalactic medium. This space between galaxies is not a perfect vacuum. It contains a sparse fog of primordial gas, the very same hydrogen and helium that first filled the universe. For molecules to exist out here against all odds, they would need to form in near total isolation, far from the protective cocoons of dust and the crowded gas of galactic disks. The primary candidate for this lonely existence is once again molecular hydrogen. Its formation in such a void would rely on the most basic and inefficient of processes, like the slow three-body association or the occasional catalytic help of a lone free electron. The challenge is survival. The intergalactic medium is flooded with the harsh ultraviolet light from countless distant galaxies and quasars, a background radiation field that constantly threatens to rip any fragile bond apart. For a molecule to persist, it must form in a tiny pocket of slightly denser gas, a remnant of a cosmic filament, and hope that the destructive photons are scarce enough to allow it a fleeting existence. Detecting these solitary molecules is one of the most formidable tasks in modern astronomy. Their signal is unimaginably faint, drowned out by the brilliant light of galaxies and the cosmic microwave background. Astronomers hunt for them using the most powerful telescopes, searching for the subtle absorption lines they imprint on the light of extremely distant quasars. When the light from a quasar billions of light-years away passes through a cloud of intergalactic gas, the molecules within that cloud absorb very specific colors. By analyzing this missing light, scientists can infer the presence and quantity of molecular hydrogen in the vast emptiness between galaxies. Why does this matter? Because these diffuse molecules are cosmic census takers. Finding them helps us account for the universe's missing ordinary matter, the baryons that our inventories cannot fully locate. They also tell a story of chemical pollution on the largest scale. Their presence, even in trace amounts, indicates that the elements forged inside stars have been blown out far beyond their home galaxies by supernova winds or galaxy collisions, enriching the entire cosmic web. This intergalactic molecule hunt reveals that chemistry is not a local phenomenon, but a universal one, a faint signature of structure that connects the entire cosmos. Supersonic turbulence ripped through the primordial gas, a chaotic force that became an unexpected architect of chemistry. In the calm between star formations, chemical reactions proceeded at a glacial pace. But when a shock wave born from a supernova blast or a galactic collision slammed into a cloud of hydrogen, it created a violent pressure cooker. The shock front acted like a cosmic snowplow, ruthlessly compressing the diffused gas. Atoms that had drifted light-years apart were suddenly forced into an intimate, chaotic crowd. This rapid compression did more than just bring atoms together. It violently heated the gas to thousands of degrees. In this superheated, high-pressure environment, the rules of chemistry changed entirely. The gentle, slow dance of molecule formation was replaced by a frenzied stampede. Particles now collided with immense force and frequency, their thermal energy easily overcoming the activation barriers that would have blocked reactions in the cold. Molecular hydrogen, which took millions of years to form in the quiet dark ages, could now be forged in an instant. The shock wave did not just create the simple H2 molecule, however. This violent environment was a crucible for complexity. The intense heat could break the sturdy bonds of carbon monoxide, releasing oxygen atoms that could immediately bond with hydrogen to form water vapor. Simple molecules were shattered and reassembled into new, more complex forms in the turbulent aftermath. We can see this process in action today within the gorgeous, expanding remnants of supernova. The delicate filaments of glowing gas are not just a testament to destruction, they are active chemical factories. Shock waves ripple through these nebulae, compressing and heating the stellar debris, triggering rapid rounds of molecule building in the most unlikely of places. This violent process reveals a fundamental truth about the cosmos, that chaos and destruction are often the very forces that build the foundations for new creation. Massive objects in space can bend light like a lens, and this natural phenomenon may have given us an unexpected window into the chemistry of the first galaxies. When the light from an incredibly distant, ancient galaxy passes near a massive foreground object like a galaxy cluster, its path is warped and magnified. This effect, called gravitational lensing, acts as a cosmic magnifying glass. It can take the faint, whisper-thin signature of molecules from a galaxy at the edge of time and amplify it, making it bright enough for our telescopes to detect. Without this natural assist, the light from those first molecular clouds would be far too dim for us to observe. It is like trying to read a message written in faint pencil from a mile away, and then someone hands you a powerful telescope. Suddenly, the words become clear. This lensing effect does not just make the galaxy appear brighter, it can also stretch the image, smearing it into a luminous arc. Within that stretched light, the specific absorption lines of molecules like carbon monoxide or water become more pronounced and easier to analyze. This allows astronomers to do more than just confirm the presence of molecules. They can start to map the chemical composition of these infant galaxies, understanding where different molecules are concentrated and how they interact with the nascent stars. This gravitational amplifier is letting us peer into the chemical nurseries of the very first galaxies, observing the foundational chemistry that would one day lead to planetary systems and life. What other cosmic illusions might be hiding the deepest secrets of our origins? Our journey through cosmic chemistry rests on a single, powerful foundation, the Big Bang. Yet the universe is a place of endless possibility, and our dominant model has always faced compelling alternatives. Consider the steady-state theory, a once formidable challenger. In this vision, the universe had no beginning and will have no end. It is eternal and infinite, with new matter continuously created to fill the voids left by expansion. There is no primordial fireball, no single moment of creation. So how would the first molecules form in such an eternal cosmos? There would be no universal first molecule at all. Instead, molecules would be forming all the time, everywhere, in a continuous process. The creation of hydrogen and helium would not be a one-time event from a hot, dense state, but a slow, steady trickle of new atoms appearing in the vast spaces between galaxies. Molecular hydrogen would then form in localized regions within the same dark clouds we see today, but the timeline is stretched to infinity. There is no dark ages, no first star, just an endless, steady cycle of birth and decay. Another radical alternative is plasma cosmology, which views the universe not as dominated by gravity and dark matter, but by electromagnetic forces acting on hot, ionized plasma. In this electrically charged cosmos, the formation of the first molecules would be a violent, filamentary process. Vast currents flowing through space would pinch the plasma into twisting ropes and sheets. Within these cosmic power lines, the intense electromagnetic forces would compress and heat the gas, forging molecules not through slow, cold accumulation, but in the searing flash of electrical Z-pinches. Helium hydride might form readily in these stellar-like sparks, not in a cooling universal plasma. The very first molecular bonds would be the product of cosmic lightning, not a fading cosmic glow. These alternative visions are not just historical footnotes. They serve as a crucial reminder that our entire story of the first molecules, from helium hydride to the hierarchical growth of galaxies, is built upon the framework of the standard cosmological model. That model is spectacularly successful, supported by a wealth of evidence from the cosmic microwave background to the abundance of light elements, but science progresses by testing its foundations. Every observation of a distant molecule, every map of the cosmic web, is simultaneously a test of our core assumptions about the universe's origin and evolution. The search for the first molecules is, in the end, a search for our own cosmic context, a quest to understand which of these grand narratives truly wrote the chemical recipe for reality. But this entire cosmic story rests on a razor's edge. The very laws of physics that allowed for the first molecules appear to be perfectly calibrated for a chemistry-rich universe. This brings us to a profound and philosophical theory, the anthropic principle. The idea is startlingly simple. For molecules like helium hydride or water to ever form, the fundamental constants of nature had to be set to incredibly precise values. The strength of gravity, the force of the electromagnetic interaction, the mass of a proton, all of these are dials that, if turned even slightly, would have resulted in a sterile cosmos. Imagine a universe where the strong nuclear force was just a few % weaker. Protons and neutrons would never have stuck together to form the nuclei of hydrogen or helium in the first place. There would have been no atoms, no periodic table, and certainly no molecules. Conversely, if the electromagnetic force were significantly stronger, electrons would bind so tightly to their nuclei that atoms would be tiny, inert spheres, never sharing electrons to form chemical bonds. The delicate balance that allows for a carbon atom to exist, for water to be a universal solvent, and for stars to burn for billions of years seems too perfect to be mere chance. This apparent fine-tuning forces a difficult question. Are we the beneficiaries of an astronomically unlikely cosmic lottery ticket, or is there a deeper reason? One compelling answer lies in the theory of a multiverse. In this view, our universe is just one bubble in a vast, perhaps infinite, cosmic foam. Each of these universes could have its own random set of physical constants and laws. In the overwhelming majority of them, the numbers are wrong. Those universes remain empty or form only to collapse instantly, or produce no structures more complex than a hydrogen atom. But in a vanishingly rare subset like our own, the numbers by pure chance allow for atoms, molecules, stars, planets, and observers. We find ourselves in such a universe not because it is special, but because it is the only kind of universe in which beings capable of asking the question could possibly exist. The alternative is even more mind-bending. Perhaps this fine-tuning is not random at all, but points toward a deeper, unified law of physics we have yet to discover, a single principle from which all these seemingly arbitrary constants naturally emerge. The search for the first molecules, then, is more than a historical quest. It is a test of reality itself, probing whether our existence is a glorious accident or an inevitable consequence of a cosmos built for chemistry. These grand questions of fine-tuning and cosmic origins are no longer confined to theory alone. The James Webb Space Telescope and the Atacama Large Millimeter Array are now turning speculation into observation. Perched 1,000,000 miles from Earth, the Webb telescope acts as a perfect time machine. Its infrared eyes are uniquely tuned to peer through cosmic dust and see the light from the first galaxies and stars, light that has been stretched into infrared wavelengths by the expansion of the universe. It is hunting for the specific chemical fingerprints of those earliest molecular clouds. Scientists are directing its gaze at the most distant quasars, using their brilliant light as a cosmic flashlight. As that light passes through ancient gas clouds on its journey to us, molecules in those clouds absorb very specific colors. Webb is exquisitely sensitive to the absorption lines of molecular hydrogen, and potentially the faint whisper of helium hydride in regions re-ionized by the first stars. Simultaneously, down in the high deserts of Chile, the ALMA array is performing a different kind of magic. Its dozens of radio antennas work in concert to detect the faint radio waves emitted by molecules as they tumble and vibrate in space. ALMA is not looking for the very first bond, but for the complex chemistry that followed. It is mapping the distribution of water, carbon monoxide, and complex organic molecules in the dusty disks around young stars, the very places where new planetary systems are being built. One of its most exciting campaigns involves peering into the hearts of distant, lensed galaxies, those smeared arcs of light magnified by gravity. There, it searches for the spectral signature of hydrogen deuteride, that cosmic fossil molecule. Finding it in such ancient environments would give us a direct measurement of the temperature and density of the gas, just as the first galaxies were assembling. This is not passive observation, it is an active interrogation of our cosmic past. Every data point from these magnificent instruments is a test, challenging our 30 theories and refining our story of how a barren cosmos became a chemical universe. The answers are no longer hidden in the past, they are streaming down to us now, one photon at a time. From that single bond of helium hydride to the vast organic clouds of deep space, our chemical universe has unfolded in an epic of cosmic evolution. We have traced 30 compelling theories, from the quantum tunneling that defied the cold to the violent supernova that forged new elements, and from the silent work of interstellar dust to the magnetic fields that shaped stellar nurseries. Each theory offers a vital piece of the puzzle, explaining how a barren cosmos became a chemical cradle. Yet for every answer, new questions emerge. The story of the first molecules is not a closed book, but a living narrative being rewritten with every observation from powerful new telescopes. We want to hear which of these theories captured your imagination the most. Was it the lonely pioneer helium hydride, the quantum magic that built bonds from nothing, or the dark matter halos that provided the first safe haven? Share your favorite in the comments below, and if you enjoyed this journey to the beginning of everything, subscribe for more deep dives into the mysteries of the cosmos.